All right, let's just dive right into this explainer. If you're gearing up for your Mathematic I exam, you already know eigenvalues and eigenvectors are an absolutely massive topic. But don't stress, we're going to break this whole thing down together. Today, it's all about finding those principal axes, and by the end of this, you'll have a totally rock-solid, step-by-step method to just crush these problems.
So I want you to start by holding this kind of wild geometric idea in your head. Imagine a specific direction where a matrix only stretches or shrinks a vector, but literally never spins it. Usually when you multiply a vector by a matrix, it gets knocked way off its original path, rotated, skewed, you name it. But what if there are these hidden special axes where the matrix acts just like a basic number, just pulling the vector further out or pushing it closer in? Well, that exact direction, that's our eigenvector. And the stretch factor, exactly how much it scales by, is the eigenvalue. This is a massive shortcut for understanding really complex transformations. Instead of looking at some messy matrix that warps space in all sorts of crazy ways, we just find its principal axes. The matrix literally only scales these axes. Once you find them, boom, you've unlocked the fundamental DNA of that matrix. Okay, here's our agenda for today. 1, the intuitive hook. 2, deriving the equation. 3, the 3x3 matrix walkthrough. 4, finding the eigenvectors. And 5, our recap and engineering applications. Let's get to it. Section 1, deriving the equation, from concept to formula. So this brilliantly shows how the math actually flows. We start right at the definition. Matrix A times vector V equals a scalar, lambda, times vector V. Now, we want to solve for V, right? So we try to pull everything over to one side. But wait, you can't just subtract a scalar from a matrix. That's a total math crime. So we introduce our trusty identity matrix E. Now we've got A times V minus lambda times E times V equals the zero vector. We factor out that V, which gives us our foundational linear system. You absolutely need to lock this final equation into your memory. Parentheses, A minus lambda E times V equals 0. Now here is the absolute crucial point. We have a matrix times a vector V equaling 0. If that matrix is invertible, the only solution is V equals the 0 vector. And, well, a 0 vector tells us absolutely nothing about our principal axes. It's just what we call the trivial solution. To actually force a real non-zero vector out of this system, that matrix cannot be invertible. And the only mathematical way to guarantee that, set its determinant exactly to 0. That trick right there, setting the determinant to 0, is literally your golden key to finding eigenvalues. Moving right along to section 2, the 3x3 matrix walkthrough, finding the characteristic polynomial. To actually set this up, we take our given matrix A and we simply subtract our variable, lambda, straight down the main diagonal. Literally, that's it. We leave every single other number exactly as it is. That resulting determinant is called our characteristic polynomial, or P of lambda. So your immediate goal on the exam is to expand this determinant. To compute it, we're going to expand straight down the first column. We multiply the entry from row 1 by its corresponding 2x2 determinant. Then we do the exact same for the entry from row 2 and then row 3. But hey, watch out here. Remember your alternating signs going down the column. Plus, minus, plus. Seriously, take a deep breath on this step during the exam. This is where almost all the silly arithmetic mistakes happen. So write out your steps really clearly. Once you do the algebra, multiply the whole shebang out and set that resulting polynomial to 0, you unlock your distinct scaling factors. For this specific matrix we're looking at, the roots of our polynomial actually fall out really nicely. Lambda 1 is 2, lambda 2 is 3, and lambda 3 is -1. Those three numbers, those are our eigenvalues. They're the exact stretch factors along those hidden principal axes we talked about earlier. All right, section 3, finding the eigenvectors, solving the linear equations system. So let's take lambda equals 2. We subtract 2 directly down the diagonal of our original matrix, which gives us a brand new linear equation system. From there, we just use your standard Gaussian row operations to simplify it into stepped form. And look at that. Notice how the bottom row becomes all zeros? That is absolutely perfect. It proves our determinant was in fact 0, meaning we're perfectly on track to find a non-trivial solution. Because we got that row of zeros, our matrix has a rank of 2. But hey, we still have 3 variables. This means we have one free parameter. We can just set our third variable, x3, to a parameter. Let's just call it t. When we back substitute t into the rows above it, we figure out that x2 equals 0 and x1 equals t.
So the eigenvector isn't just a single point in space, it's an entire line. It's a whole-scale direction represented by any non-zero number t multiplied by the vector 1, 0, 1. We actually call this entire space the eigenrealm.
Finally, Section 4, Recap and Real-World Engineering Applications. Okay, here is your ultimate exam survival guide. If you just memorize this 4-step algorithm, you're going to confidently navigate literally any eigenvalue problem they throw at you. Step 1, set up the matrix with lambda subtracted straight down the diagonal. Step 2, find the determinant to create your characteristic polynomial. Step 3, solve for the roots to get your eigenvalues. And step 4, plug them back in and use Gauss to find your eigenvectors. That's it. That is the whole game. But, why do we actually care? Well, as noted straight out of your mathematics materials for civil engineers, these abstract numbers govern some pretty intense physical stuff. The text basically translates to eigenvalues play a role in things like the stability of bridges and the roaring vibrations of motors. So the math you're writing on your paper literally translates into finding the principal axes of stress that stop a whole structure from just collapsing. Think about it. Eigenvalues often represent resonance frequencies. If some external force, say wind hitting a bridge or the hum of a giant engine, matches one of those eigenvalues, the whole system is going to vibrate uncontrollably along its eigenvector until it literally breaks. Finding these numbers tells engineers exactly which frequencies they absolutely need to dampen. So, the next time you drive across a stable bridge or hear an engine just purring smoothly, ask yourself, how are those hidden eigenvalues doing all the heavy lifting to keep everything from shaking apart? Because the math you're practicing right now, it's the exact same math that builds the entire modern world. Good luck with your exam prep. Keep drilling that 4-step method, and we'll see you in the next explainer.